All right, so today I'm going to be talking about the double slit experiment. So the first prerequisite that we kind of have to look at is how light waves interfere. So if you have, let's say, a light wave right here, like so, you want to see how another light wave interferes with it. Let's say, let me grab a different marker, that these waves are both in the same phase, and that let's say they're released at the same time or the same spot. And so they're basically going to be identical, kind of right on top of each other. These waves, obviously they're the same wave. You really just have 2 times the wave, so they're going to constructively interfere. And so the resulting wave, if you add up the wavelengths, add up the amplitudes, you have this plus this other red one, which I'll use in a different marker. So it'll look like this. Wave's going to be up here. And then for this one, you have, actually let me add this little center line. You have this plus this, and then the same thing here. And then you're just going to repeat this basically for the rest of the wave. So you're going to have a point here and a point here, and then at these points where they're both 0, they're both going to be 0. So you're going to have these nodes, and the resulting wave is going to be the same frequency except just scaled upwards. So how much would I have to move this red wave to have it still constructively interfere? Well, I want to move it to where the waves are basically starting at the same spot again. And so if I erase it and redraw the wave, I'll draw this black wave first. Originally, I started the wave right here. Let's say I want to start it right here now, because they will still constructively interfere. How far away did I start this wave from where I first started it? Well, if you look at this here, it's from peak to peak, that is 1 wavelength. I could do the same by starting it over here, and that distance would be another wavelength from here, or from the starting area, 2 wavelengths. And so I know that if I start this other wave pulse from either 0 wavelengths or 1 or 2 or any integer number of wavelengths, then I will get constructive interference. Now, let's say I want the waves to destructively interfere. Instead, what I'm going to do, and let me just write this as a little note in the top right over here, where n lambda constructive if I have this wave again, let's say I want the waves to destructively interfere, I'm going to do a phase shift by pi radians or 180 degrees. Instead of starting it up here, I'm going to start it, say, right here. And so I'm going to draw a wave like this. Now, at all of these points, you see the peaks and the troughs are going to cancel out, and so you're just going to get 0 amplitude wave everywhere. You're going to have complete destructive interference. And so what if I want to move this? Well, where is this already? This is a half wavelength because it's from peak to trough. And so this is lambda over 2. It would also work if I started the wave not right here, but right here. This is 3 lambda over 2, and so on and so forth. And so I would be moving this by half wavelengths instead of even integer wavelengths. So for any lambda where it's lambda over 2, 3 lambda over 2, and so on and so forth, obviously it's the same pattern for this. I'm adding a wavelength each time because it's going to restart the cycle, right? If I have an angle theta right here, if I rotate it by 360 degrees, I'm going to get the same angle. So it's the same thing here. And so this is going to lead to destructive interference. And so this is where I introduce the concept of a wavefront, and all this is going to prepare us for the double slit experiment, I promise. Normally, you draw a wave like this. You have your center line right here. This is most commonly the x-axis and the y-axis, sometimes y and t, just however you're modeling it. And this right here is your peak. And this right here is your trough. And then the distance from one peak to another is the wavelength. Now for wave fronts, it's kind of like when you drop a rock in the water or like a pond and then it ripples outward. You have your little source and then you have your wave fronts. What these wave fronts are is they're perpendicular to the direction that your wave is traveling. If this wave is going outward, each wave front, this right here, is perpendicular to the direction of travel. And so what do these wave fronts represent? Well, they represent the peaks of the wave. And so since these represent the peaks, that means the distance between them represents the wavelength. And then that means this little middle point in between, and actually I'll use a different color so it's easier to distinguish. With this little dotted line, or actually I'll just make it a straight line, that's where the trough is. So you can almost think about it as like, it's up, and then it's down, up, up. It just keeps on going. So now that I've kind of introduced that idea of a plane wave and how the peaks, troughs, and wavelengths relate to that, now I'm going to set up the double slit experiment. So, use a ruler so I can get some straight lines. Let's say I have a wall right here. In this wall, I have two slits that are, roughly the same size. And then over here, I have another wall. Now, if on this side, I have a source right here, and I'll label that source. I send out a wave pulse. There's going to be these wave fronts right here. And, when this meets the wall, it's just going to bounce off the wall. It's going to reflect, do whatever, right? But when it meets these slits over here, it's going to radiate outward like this. Why? Because, it's going to hit the sides of the slits right here and it's going to diffract outwards. It's going to radiate. Same thing with this. Now, there's all these spots, and obviously I drew wave fronts here, all these spots where the waves are interfering. And then I'm also, real quick, just going to draw the troughs of the waves with these little red dots. I know there's a lot going on in this model already, and I already just started drawing it. But at all the points where these wave fronts, the crests, overlap, we're going to get constructive interference. I drew this kind of poorly, but basically from here we're going to get a straight line, and then these all overlap over here. And so from here we're going to get a straight line. And then in the middle here you can see that all of these overlap, and we're going to get a straight line. Everywhere where all these little points overlap, we're going to get straight lines, and they're going to point towards the wall right here. And where these waves are going to be the most intense is going to be where there's the most constructive interference, aka where there's the most wave fronts that are interfering with each other. And so the more and more the wave spreads out, the less they interfere. And so you'll get this kind of curve here of the intensity. And it's going to be higher in the middle, and then it's going to be lower here, and then it's going to be lower here, and so on and so forth. And you're going to have this little, it's almost like a graph, just of the intensity of the wave that's on this wall. And so how can I use where there's the peaks and the troughs, and I almost forgot to mention the troughs. As you can see, each spot where there's the troughs, which is the little dotted red lines, that's going to be in the middle of these. Each spot where that interferes with, if you just draw this out more, you can see there's spots where the wave fronts of one wave interferes with the troughs of another wave. And that's where, these are going to cancel out. And so there's not really going to be any intensity over here. It's going to have destructive interference. And that's why you're not really going to see any bumps over here. It's just going to be straight on the wall, not really any intensity. But anyways, you're going to have your peaks and you're going to have your troughs. And the one in the middle is going to be the largest in intensity. And for the path difference, now what is the path difference, right? Let me erase this diagram. I'm just going to draw something a little bit simpler, so that way we can focus on just a single spot. So I'm not going to use a ruler this time. You have your two slits, right here and right here, and you have your wall. And let's say I just have a source. Let me choose this point P right here. And we'll say, there's this peak in the middle, and there's this over here. Let's say this P is where there's a spot of constructive interference, right? And so I have this wave 1 going to point P, and I have this wave 2 going to point P. As I said earlier, or take this diagram from earlier that I had first introduced, where you have the waves on the line, and you start them at the same point, or you start them a wavelength away, or 2 wavelengths away, or an integer number of wavelengths away, and they're always going to have the constructive interference. This has that constructive interference, and so we know that the difference in where these two waves start, or how much they travel, on this x direction, is going to be an integer number of wavelengths. Now obviously here, if you take this central line right here, if I take this spot, these 2 points are going to travel the same distance to get here, and so that's them starting at the same spot, right? That's 0 wavelengths. And so then it should follow that this second spot of constructive interference, that means the difference in the path that these 2 waves take. These 2 lines right here, the ones going to point P from each slit, the difference in the path that the waves take, so let me redraw this. I know I'm doing that a lot, but just for clear visualization. The difference in the path that each of these waves take to this point P, and that's represented by this little distance right here. According to this should be 1 wavelength. So yeah, if you have the path difference, which is the wavelength, you could figure out the path difference, which is, how much longer this wave has to travel to get to that point. But what is that really useful for, obviously, right? We know that from this, but what does this mean? What can we use this to find? Well, let's say we have our 2 slits, and between the 2 slits is a distance right here, which I'm going to call d. We use lowercase d. Using geometry, we can actually figure out the distance of this d based on the wavelength of the wave. We know that if we do our slit experiment, we're going to have our little pattern right here. So we're going to have our peak in the middle, our peak over here, and then one over here. And it's going to, disperse out, and the peaks are going to get smaller. But we don't really care about that. What we care about is the wavelength. And to find the wavelength, we do what we just did. We take some point, P, and we fire each of these to that point. And we know that the path difference, which I'll call delta x, at least for this point right here, we know it's 0 here, but we can say it's lambda, right? Based on what I started out with at the beginning of the video. And we can use some geometry here. We can draw a line from this little center part where this horizontal line lies. We can draw a line from there to point P. We can take this angle from the horizontal to point P, and we can call that theta. And we also have this little triangle here. We have the spot where this intercepts the x-axis. You can draw a little line there. That's parallel to the line from this hole to point P. Now stay with me here. This gets a little bit complicated, but I'll try and explain it as best I can. I'm still learning this too. To find the path difference, which we know right here is lambda, what we do is we construct a triangle. We say that this right here, this is point P. This is, the middle of our distance between the slit. And then this is, the point where the wave is the highest, the intensity is the highest. We know this is theta. Then we take our point here. We know that our distance to this here is lambda. And we make a vertical line like this. We know this goes to the other slit right here, which we'll call slit 1, and we'll call this one slit 2. We know that the distance from 1 to P is this, and so we made a little triangle here. Now, if you think about it, this triangle here, let's see. Just thinking about this one. If this angle here is theta, then this angle here is, obviously 90 degrees minus theta. And so it should follow that to make 90 degrees here, to make 180 degrees here, we know that this is a right angle, and we know that this is a right angle. And so we know that these two angles should add up to 90. No, that's not right. Give me a second. I just did this earlier. But I forgot how I did it. If you have, the hardest part about this derivation is just the geometry. So you have your distance from the middle, call this M, it's our midpoint, to point P. You have our angle theta. You're trying to find this little line here. This is going to be at the center here. This is slit 1, which we'll call S1. And this is slit 2, which we'll call S2. And you have our triangle, which is basically just this distance right here. This is your right angle. Okay, so now I get it. If you make a triangle, let's say, just give me a second, probably have to edit this out. This is tough. Oh, I got it. This right here is an angle theta, and this is a 90-degree angle, obviously, right, from the horizontal. So that means this angle right here of this triangle is 90 degrees minus theta. And we know that this angle right here must also be theta. And so then we can take this triangle. It's a really poor visualization, I know. And we have this triangle right here. And we say that we have this right angle, we have theta up here, we have our delta x, which is lambda down here. And then this is d. This is obviously the distance between the slit. This is lambda. Because we know this is theta. And this triangle right here is this big triangle. We use this to solve for d using some basic trigonometry. You can use sine as, I believe, opposite over hypotenuse. Yeah. So sine of theta equals, what is that? Lambda over d. And so then let me erase this because this is clutter. We can then rearrange this to find d. We can say d equals lambda over sine of theta. Or if you know d already and you want to find the wavelength of the wave, you can do lambda equals d sine theta. So if you have one, you can solve for the other. That's kind of the importance of the double slit experiment. That's what it's used to measure. If you use something, like a really small distance and some sort of atomic structure, like on the order of, nanometers or even smaller, right? You can use the double slit experiment to find distances or wavelengths or whatever you need to find. That's basically the significance of what this is. So yeah, I'm going to recap everything because I paused a few times and my explanation was a little bit faulty. So I'm just going to try and really bring this back here. To summarize, you have your wave, and if you have another wave, and for simplicity, all the waves that I've mentioned in this video have been in the same phase, meaning they have the same frequency, wavelength, all of that. If you want constructive interference, you could either start them at the same place. Actually, that's not really what I drew. You can start them at the same place, or you can start them a wavelength away, or 2 wavelengths, or any integer number of wavelengths, and you'll get constructive interference, adding up into wave kind of like this. And so it follows that when you have 2 wave fronts that interfere from the double slit experiment, you have your first wave coming out of your first slit. It's going to be like this. And then you have your second wave coming out of your second slit. Boom, 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 boom. In the middle, they're going to interfere the most. That's where you're going to get your biggest pulse. And then looks like there's some interference over here a little bit, but just a bit though. So obviously this is a bit smaller. And then there's a little bit over here. So it's just a bit smaller. And as you go on both ways here, it gets a little bit smaller. What gets smaller? The intensity of the wave, aka kind of the size of this little hump on this axis, right? And then using some geometry, you can come to the conclusion that if you have 2 waves in your double slit and you want them to go to some point P, and the difference in the path is going to be, well, you have your center line right here. If this is, 1 hump away from the center, then this distance is 1 wavelength. If you have your point P, let's say over here, then the distance is going to be 2 wavelengths, and etc. It's basically the same thing that was up with this wave, where you could start another one here, you could start another one here, and you just keep going into your number of wavelengths to get your constructive interference. And once you figure out the geometry for that, that culminates into the equation of d, the distance between your 2 slits, this is d, times sine of theta, which is, if you go to some point P, your angle from the horizontal, that's equal to your difference in path, which is the difference right here, delta x. And this, which we get from this earlier representation of the wave, is an integer n times the wavelength lambda. And that's how you can solve for either the distance between your 2 slits or the wavelength of the wave you have. Or even the angle if you already have both of these. Yeah, that's about it. If you have any questions, let me know in the comments below and I'll try and answer them as best I can. I know this is a more advanced topic, but I'm hoping to learn more about it myself, and I'm hoping you all can too. Thanks for watching.